Okay, let's start. Do you have any questions? Okay, so if not, then please keep in mind that your first midterm will be next Friday during class time, which is right now. It's only an hour, 20 minutes or 80 minutes. So the first 40 minutes can be, for office hours, in which you can come here, ask questions, whatever. But basically on Friday, okay? So you won't have any class, but there'll only be exam. What else? So we'll talk more about that toward the end of the class. You should have received the announcement, right, about the, basically the rules and guidance, right, guidelines for the exam. Well, anyway, right, we'll speak more about that toward the end of the class. Okay, so to continue with what we did last time, we were talking about, so we're almost done with chapter 2, right? The title there, right, is random variables. And so the topic that we were discussing was moment-generating function. Okay, or MGF. So the first thing, right, is that the moment-generating function of a random variable or random variable x, right? Then phi sub x of t will be defined as expectation of eta tx, okay? And there are basically two, right, use of a moment-generating function. The first is just basically to calculate moments, right? And we explained last time how basically if you differentiate, right, the moment-generating function, then you can exchange differentiating and integrating. And since you're differentiating with respect to x, basically this is x, right, e to tx. And so if you plug in, right, t equal to 0, then, right, that's just expectation of x. And so on, right? So basically, if you differentiate n time, then the derivative, sorry, that's the nth moment, okay? Now here, sometimes you cannot plug in 0 directly. So the key or the rule actually is limit as t goes to 0 of, right, the derivative. You may not be able to plug in 0 directly, as you'll see soon. And that will give you the nth moment, okay? And so let's look at an example real quick. So the example is one of your homework problem, right? I forgot which one, but basically it says that let consider a uniform, right? 0 to 1. Okay, random variable. The first thing is to calculate the moment sharing function of x, right? So let's do that first. All right, so what's the answer here for a uniform? Well, if you, right, multiply this with the PDF of the uniform, which is 1, right, from 0 to 1, then you clearly see that's just going to be that, right? Okay. So that's the moment sharing function of a uniform random variable of uniform 0 to 1. So the key, right, is to what the question asks you to calculate the expectation and the variance of, right, the uniform using this technique. As you will see that basically, so even though this is classified as a use of a moment sharing function, in reality it's a little bit tedious, okay, to carry it out in terms of calculation. So it more or less remains as a theoretical tool to use rather than an application, like a real computation application. So here, right, as in the homework, we'll just be limiting ourselves to calculating the expectation, okay? The derivative, right? Yeah. Okay. So what difficulty do we have when we try this technique with this approach, of course, or there's no difficulty? Well, so what's the derivative, right? the derivative of this function, right, is, well, a prime b minus b prime a over b squared, right? So, well, I mean, even though, right, this is like kind of like the generic instruction or this, right? You can see that, of course, plugging in 0 directly in here is, without is not an option, right? So we need to take a limit as t goes to 0 of this expression. Now, what is this limit as t go to 0? What's the answer? So basically, right, this is a 0 over 0 scenario. So you use L'Hopital's rule, right? So you got t e to the t minus e to the t, or sorry, plus e to t, right? And then minus e to t over 2t. And right, clearly that's just e to t over 2. So that's 1/2. Okay. Now, which is of course, right, correct, because if you just do it the usual way, which is, right, the integral x, right, dx, you get 1/2. So of course, right, this is a much more, let's say, painful way to calculate expectation of a normal random variable. Okay. On the other hand, it just meant, okay, to explain or demonstrate that yes, okay, you can calculate the moment of a random variable using this technique. But of course, right, in general, this also demonstrates that the process, well, especially differentiation, right, is tedious to carry out in general, because you will end up with like product rule or quotient rule, right, with many terms, and the more you differentiate, the more terms you pick up. So, for example, right, if you have to calculate the variance as the problem asked for, then the second derivative, right, will involve more terms than the first derivative, and it's just in general like kind of not very pleasant, right, to do this kind of problem. But anyway, so that's a demonstration. Any question? So the second use, right, of the moment-sharing function is to, and that is a much more important role, is to identify, right, random variables. And so basically, you can recap like this. If you have two random variables who has the same moment-sharing functions, then they must be the same random variable. Okay. This notation means they have the same distribution, right? And be very careful, we are not saying two random variables are equal. We're saying that they are equal in distribution. For example, right, if you toss a dice twice, then the first toss and the second toss are not equal, right, in general. However, the first toss and the second toss are equal in distribution. They're both uniform, right, 1 to 6. Okay, so basically it says that if you can identify, right, the moment-sharing function of a random variable, then you can tell what it is. So an application, right, that we talked about last time is the result, which is super important for us in this class, that if you have two independent Poissons, you know what, let me just call it x1, x2, right? You have two independent Poissons. Then if you sum them up, you also get Poissons. All right. So before, right, so we proved this last time, we'll prove it again. But before we prove this, okay, let's just appreciate this result real quick by asking a similar question like this. Suppose you have independent uniform, right? If you have two independent uniforms, it's a sum, a uniform random variable. Yes or no? Well, the answer is no, right? If you have two independent uniforms, then the sum will have this kind of distribution. All right. So this is the density of the sum of two uniforms, which is clearly not uniform, okay? And so basically, the fact that you can sum two random variables of the same family and you get back the same family is, as far as I know, extremely rare. The only other similar random variable is the normal, okay? If you sum up two independent normals, you get a normal random variable. In general, right? You have to be super careful when you sum random variables on what you will be getting in terms of the distribution. All right, so, but how do you prove, right, this result? Well, again, right, do remember that summing random variables in general is a, let's say, complex business, okay? Like taking expectation is easy because it's linear. Taking variance, well, I wouldn't call it easy, but let's say it's not as challenging, especially when you have independent random variables, and it's also easy because variance of a sum is sum of variances. But even when you have independent random variables, finding the distribution, okay, meaning either the probability distribution function or the PDF, can be, let's say, complex task. It depends on what, what random variables you have to start with. The more complex these guys are, the more complex the sum should be. And in general, right, the technique of moment-sharing function is best suited for this kind of question. Well, what's the reason, right? The reason is if you have independent random variables, okay, in general, then you look at the moment generating functions of the sum, right? Then the exponential will split, and then this will be, by independence, the product of these two terms, which turns out to be the individual moment-sharing function, right? In other words, moment-sharing function of the sum is the product of the individual moment-sharing functions. So again, it's extremely easy to do this kind of thing if you know, right, what the original moment-sharing function is. And we went through this calculation last time, right? If you have a Poisson, let's say lambda, then the moment-sharing function, right, will be as follow: e to minus lambda, e to tk, right? E to minus lambda, lambda to k over k factorial. And then e to minus lambda can come out, e to tk can come in, and then thus, right, the sum of an exponential. So we got e to the lambda e to t, which is e to the lambda e to t minus 1. Okay. So that's the moment-sharing function of a Poisson. And so when we have two independent Poissons like this, then the moment-sharing function, right, as we explained above, is the product of individual moment-sharing functions. And then, right, each of them is of this. And right, by the property, right, of the exponential. And therefore, right, by the general remark that moment-sharing function, right, is unique in terms of, identifying, right, the distribution, and this must be a Poisson random variable with rate lambda 1 plus lambda 2. And again, right, the fact that sum of this Poisson will be extremely important to us in the future. So one of your homework, right, deals with this. This is question 4. So it says that the number of traffic accidents on successive days are Poissons, are independent Poissons. With rate 2. Okay. Okay. So question A asks for find the probability that 3 out of the next 5 days have 2 accidents. All right. So how do we do this? What is this probability? So the setup, right, is that you have 5 days. Each day, right, the number of accidents is Poisson. Okay, and they're the same kind of Poisson. I mean, same distribution, and they're independent. And then we ask, out of 3 out of 5, we have 2 accidents. So the first thing to do is to look at a probability of 2 accidents, right, on any day, right? And that will be what? Since it's Poisson 2, right? E minus 2, 2 over 2 over 2 factorial, right? So that's probability of 2 accidents on a day. Okay, let's call it P. It's a number. Now, 2 accidents on consecutive days, right? I mean, on each any of the days, I guess, right, are independent. So therefore, 5 days here, the number of accidents are actually like a binomial random variables, right? When we look at the number of success, where success here in quote is having 2 accidents. So the answer, of course, right, is 5 choose 3 P cubed 1 minus p squared. Any question on this? All right. Next question. Find the probability that there's a total of 6 accidents over the next 2 days. All right. So how do we do this problem? So the keyword here is total, right? Total refers to sum, right? So this is a Poisson, this is a Poisson, right? The next 2 days. When you sum Poisson, you get some independent, right? Poisson, you get a Poisson, right? And that's the key here, okay? And so we can say that, right, by, right, the result, or you can just write down, right? Let x1, right, be the number of accidents on day 1. Okay, let I be number of accidents on day I. Then x1 plus x2, right, by being independent Poisson, will be Poisson, right, 2 plus 2, right, which is Poisson 4, of course. So therefore, right, they ask for 6 accidents. So probability x1 plus x2 equals to 6 is e to the minus 4, 4 to the 6, over 6 factorial. Any question? All right. Next one. If each accident is independently a major accident, with probability P, find the probability that there's no major accident tomorrow. How do we do this question? All right. So first of all, right, this is a very popular type of question that basically it talks about, so Poisson, remember, is kind of the model for arrival of events, okay? So here event is traffic accidents, right? So a further elaboration of the model would be between among the events, they can have different types, okay? So here, right, the type is, I guess, a major or minor accident, okay? But I guess a kind of example, this is just to show you, let's say that, you know, let's say people go to a gym, right? It's a Poisson, whatever, okay? You can just throw in a rate here, a day. But then among people going to a gym, the probability that a person is a male is, let's say, some rate. Okay. And then you ask for, right, among the gym attendants, let's say, probability, let's say 6 males attend the gym on a day, whatever, right? That kind of thing. That's the question, okay? So of course, right here, it's not 6, it's 0, right? No major accident, but it's similar. So basically, you have events arrival modeled as a Poisson random variable. And then you ask, well, and then you're given, right, that the events can be different types with different probabilities. So here's sort of similar to a multinomial distribution. And then, right, you asked what's the probability or what's the distribution, the number of arrival of certain types. Okay. And so let's just look at it, from a fresh point of view. We don't know anything, right? So no major accident. So how could that happen? So probability, right? So let's say X be the number of accidents tomorrow, right? We know what X is. X is a Poisson 2, right? So probability of no major accident, right, will be all possibilities of X taking on some values. Sorry, let's say this, right? No major accident. Condition on X taking on some value times probability of X taking on those values. Okay. What is this called? What is this formula called? This is the law of total probability, right? And then now when you know that there are so many accidents, right, per day, then each accident is independently a major accident with probability P. So what is the probability? This is 1 minus p raised to k, right? And then, of course, multiplying with probability x equals to k, which is e to the minus 2 to the k over k factorial. And again, right, we will bring out the e to the minus 2, leaving us with a sum. And 1 minus p can be combined with the 2, right, like that. And we recognize that this is sum of, right, the Taylor series of an exponential. So it's e to the 2 1 minus p, right? Which just so happens that the 2 cancel, giving us with e to the minus 2p. That's the answer. Any question? All right, so that's the question, right? But here I want to make one further observation that this answer is the same as the following. Is the probability that a Poisson rate 2 times p equal to 0. Okay. Well, what is 2 and what is p? 2 is the distribution of x, right? X has Poisson 2 distribution. What's p? P is exactly the probability of the major accident. So no major accident, right, is probability x 2 times p equal to 0. 0, of course, it refers to no major accident. And this is not a coincidence, all right? This actually refers to my general, right, example for you, where you have Poisson arrival, and each arrival is independently of a certain type. Then the distribution of that type, right, the number of arrivals, is actually lambda times p. Poisson lambda times p. Poisson would rate lambda times p. So the answer here will simply be the probability that Poisson lambda times p is equal to 6. And then you can write it down, right, whatever that is. Of course, right, the proof that the number of male attending the gym or the number of major accident on a day is a Poisson would rate lambda times p is a, let's say it's not a big thing, but it's something that we'll be proving, right, rigorously in the next chapter. Okay. Anyway, any question about this? All right. So let's continue with the next one. So we have shown, right, this demonstrations, right, of how a moment change function is used. Well, let's show you one more thing. This is, I don't think it's on your homework, but it's still a good question. So, sorry, not quiz 2, quiz 7. Let x and y be independent normals, mu sigma squared. So we did not discuss normal in details, but right, we're gonna look at here in this context, show that x plus y is independent of x minus y. What's the answer here? Or what would be a good way to show two random variables are independent? So, well, I mean, almost by definition, if you have this happening, for all values of little x, little y, all right, then they're independent. And the reason is this is called the joint CDF, right, of the pair xy. And if they're joint CDF split, then they're independent. Well, you could specialize it down to like something like the joint PDF split in the case of continuous random variable, or the joint, or the of course, the joint distribution function for the discrete random variables, right? Any of these, and this is the more general like kind of formulation, will show or will establish that x and y are independent. On the other hand, right, finding the joint behavior of a pair of random variables is not the most pleasant thing to do, especially when you have something like, so of course, right, I should call this U and V, whatever, but this refers to this and this refers to this. Okay. So this is just to show that, right, even though these are theoretically the tools, they're not that pleasant, okay, to use in general. And so here, the, let's say, quote unquote, pleasant tool to use is still the moment changing function, okay? And so recall that when you have independent random variables, then the moment changing function split of the sum, right, is a product of the moment changing functions. And we use this, right, to prove the sum of Poisson, right? Sum of independent Poissons is a Poisson, right? It's true for all t. So it implies this way. But what's surprising is it also goes back. Again, you just have to verify that it's true for all t, okay? It's not true for a particular value of t. But if you can prove that this identity holds for a general t, then you can prove that the pair you're looking at is independent. Yet again, right, showing you kind of how useful, right, moment changing function is. Anyway, right, so that said, we should or we must start considering moment changing function of a normal. Does anyone know what that is? So if xy are normal mu sigma square, what's the moment changing function of x and y? Well, it will be e to the t mu plus 1/2 t squared sigma squared. Okay. And it'll take probably around, let's say, 5 minutes, right, to establish this. And let's not get into it. Okay. You can kind of look up how this can be established. This is a fun calculation. It's not that hard. But anyway, right, what we're concerned with now is basically, right, to use the moment change functions to establish independence, right, of x and y. And so, one moment here. Let me try to think. I think I might have told you the wrong thing. Sorry. This is right. This is actually wrong. It's true here, but it's too weak to go back. Sorry. This is true, but to go back, we need something stronger. To prove the reverse, we need this. We sorry. I was so much into the sum. This is wrong. I mean, this is not what we're looking at. The reason is, right, the theme here is to look at independence. So you need to look at the joint behavior of the random variables. This is just about a sum. This is irrelevant. Sorry. What we need to look at, right? So let me even erase it. That's not what we're looking at. What we want is something like the joint moment change function of x and y. So the joint moment change function is established like this, right? E expectation, right, of e to the t x plus sy. All right. So you know what? Let me switch. Actually, s goes first, t goes later. Okay. So yeah, there you go. So this is basically the joint moment change function of x and y. Okay. Just like the joint density or the joint distribution function, right? So this is like the joint moment change function of x and y. If this splits, for any s and t, then the random variables are independent. What I was saying before is too weak, and it has to do with the sum. So, yeah, sorry about that. It's not going to work. It's this requirement, okay? The joint moment change function splits, then it will be independent. All right, so applying this result, right, to this problem, then well, so first of all, right, we see that from the moment change function of a individual, right, normal like this, then we know, for example, right, and by the way, let's do this. Let's suppose that x, y are independent normals, but with different means and different variance. Then, right, the moment change function of x is like this. The moment change function of y is like this. Then the moment change function of the sum, okay, x plus y because they're independent, right, will be the product of the moment-Young functions. But you see, if you multiply these two exponentials together, and the exponents add. Right. And of course, this is of the same form as the moment-Young function of a normal. So what we just established, right, is the result that when you sum independent normals, I think I mentioned this, right, when we talked about those on, then you get a normal back, okay? The reason, right, is because I will consider, right, this expression, which is the moment-Young function, right, of the sum like this, right? So in our problem, s times x, right, will be a normal with mean s times mu variance s squared sigma squared and t times y, okay, will be a normal with mean t times mu t squared sigma squared. And therefore, right, sx plus t times y will be, right, normal with mean s plus t times mu and s squared plus t squared times sigma squared, right? And therefore, the expectation of or the joint, right, the joint moment-Young function of x and y, since it's a normal random variable, will be e to the s plus t times mu. Sorry. Yeah, right. So here we can look at this, right, as the moment-Young function of a normal random variable evaluated, right, at value 1. So it's going to be e to the s plus t times mu plus, right, 1/2 s squared plus t squared times c squared. Okay. But, right, by property of the exponential, this is going to be equal to e to s mu plus 1/2 s squared sigma squared and then e to the t mu plus 1/2 t squared sigma squared. So actually, I think that's not what we're trying to prove, right? We're trying to prove x plus y and x minus y are independent. Sorry, we're not trying to prove x and y are independent. Sorry, I should have called this u and v to begin with, right? We're trying to prove x plus y and x minus y are independent. So we should plug x plus y in here and x minus y in here. Okay, sorry about that. So, sorry. All of this is actually irrelevant. I mean, what I say here is true, but it's not really what we are looking to. So hold on. So far this is useful. We'll use that. We won't need this. what we will need is expectation of e to the s x plus y, okay, plus t times x minus y. All right, like that. And see that it splits, okay, into expectation of e to the s x plus y times expectation of e to the t x minus y for all s. If this works, then s and t are, then x plus y and x minus y are independent, okay. And here, right, we'll use this general result, but with, right, x plus y. So let's see how that works, right, how this works. So we can combine, right, the x parts together and the y parts together. So here, if you look at this expression, this is expectation of e to the s plus t times x, okay? And then plus, right, s minus t times y, like that. And then, right, using the fact that x and y are independent, we can split this. Okay. And now we will plug in what this is for the x. So that's going to be e to the s plus t times mu plus 1/2 s plus t squared times sigma squared. And we'll plug this in for y, which is e to the s minus t times mu plus 1/2 s minus t squared times sigma. Okay. And now we need to check whether it's equal to this. So on the other hand, right, what is expectation of e to s times x plus y? Well, x plus y, as the result we established above, will be a normal with mean 2 mu and variance 2 sigma squared. So therefore, this expectation will be e to 2 s times mu plus 1/2 2 s squared sigma squared. Similarly, right, this x minus y will be normal with mean 0 and variance 2 sigma squared. So e to the expectation of e to t x minus y will be e to 2, so it's 0, right? So nothing there. We only have 1/2 t squared. So 1/2 times 2, right, is just, oh, let's write 1/2 times 2 here, sigma squared, okay? Which, of course, right, the 1/2 times 2 will just cancel with the 2 to give us that. So the key, right, the key is to see if this times this is equal to this times this, right? Because that's exactly what we're trying to establish. Well, see, right? So we have s mu, so that's 2s mu, right? We have t mu minus t mu, so there's no t mu. So that's e to 2s mu, right? All right. What else? What about these two terms, right? So these two terms, let's check that out, right? So 1/2, right? S plus T squared sigma squared is 1/2 S squared plus 2ST plus T squared sigma squared. And then 1/2 S minus T squared sigma squared, that is 1/2 S squared minus 2ST plus T squared times sigma squared. So when you add these two together, right, you see that you got S squared sigma squared, right? 1/2 times 2 is cancel. You got T squared sigma squared, and then this term cancel, so it doesn't show. So indeed, right, we have shown that exactly, right? This is equal to that. Sorry, this is equal to that. And therefore, right, x plus y and x minus y are independent. All right, so yeah, sorry, confusion in between where I was applying, right, the result to x and y, which obviously is independent because that's the assumption. We need to apply it to x plus y, x minus y. Any question? All right, so once again, right, this is just a demonstration of how, right, moment sharing function can be used. Again, I mean, if you're never try to explore this question and you just see my solution, you may not appreciate that it's a nice solution because after all, it takes quite a few calculations. And, you know, it's, I don't know, you have to keep straight, right? What term is what term? Well, trust me on it, or you can do it on your own. If you try to prove this using the density way, it's not that pleasant because you will have to find the joint density of x plus y and x minus y, which will lead you to the Jacobian and that kind of thing, right, from probability. Again, I don't think it's that hard either, but you have to dust up, right, the transformation, right, the Jacobian transformation and how you can put it correctly. So anyway, right, so for me, the moment sharing function is a much easier technique to deal with. All right, so let's move on to the last question that's relevant for this chapter, which is, I believe, right, the hat problem. So this one has nothing to do with moment sharing function. This one has to do with variance calculation. So n people, right, throw their hats, right, together and picked out randomly. Let x as a random variable denote the number of people with the right hats. Okay. And so we know how to work with x before, right? We split x into a sum where this sum just indicates, right, that the ith person gets the right hat, right? And so expectation of x is the sum of expectation of xi. In each of xi, right, the probability that the ith person gets getting the right hat is 1 over n, right? Anyway, right, I think we've done this question before. It says that on average, one person gets the right hat. And what's surprising, right, is this is irrelevant of what n is. N equals to 2, one person on average gets the right hat. 10 people, one person on average. 100 people, one person on average, okay? But that's not the question, right? I believe the question was to calculate the variance. And that's the question, right? What is the variance of the number of people getting the right hat? All right, how do we do this problem? So here, right, we need to use the sum formula for the variance. Okay. Now, I think we talked about how, right, the action of ith and j person, right, in the hat problem are not independent. So there's no reason why you should expect the covariance term to be 0. But on the other hand, right, it's clear that the outcome of a person in the hat problem is identical in distribution, okay, to another person. So what I'm trying to say is the xi's here, even though they're not independent, they are identically distributed, which would imply that the variances are the same. And, you know, it's similar in this way. Any pair, right, of two people in the hat problem will have the same distribution, the same joint distribution. In other words, if you look at what happens to the first and the third person, it's similar to what happens to, let's say, the second and fourth person in terms of the joint behavior. Okay. So what that means is we can reduce this down to n times the variance of, let's say, the first person, because they're all equal. You can reduce this down to 2 times n choose 2, the covariance of the first and the second person. Again, because they're all equal. Any question? So that's the first reduction. The second reduction, right? Oh, I mean, not reduction anymore. Right now, we just have to calculate this. So what's the variance of x1? x1 being a Bernoulli random variable, right? With success probability 1/n, then the variance is p times 1 minus p, right? So 1/n times 1 minus 1/n, which is n minus 1/n squared. What about the covariance term? Well, it's expectation of the product, right? Minus the product of the expectation. And we know what this is, right? Each of this is 1/n. So this is 1/n squared. And so we just have to deal with this. Now, what is this? We also talked about this before, I think, right? If each of the x is an indicator function, then the product represents the indicator of the and, right, of the two events, the joint of the two events. So this is just a probability that x1 times x2 equals to 1, or, the probability x1 equals to 1 and x2 equals to 1. All right, and we can plug this 1/n squared. So what is this? What's the probability that the first person gets his right hat and second person gets his right hat? Well, the answer is 1/n for the first person and 1/n minus 1 for the second person. All right. Like that. And let's simplify this, right? This is, so you have n squared, so you have n for the first term, right? First fraction. The common denominator is n squared, n minus 1. The second one is n minus 1, right? So you got 1/n squared, n minus 1. Okay. And so now let's plug this in. So if you plug in, you get variance of x will be, right? So your n times this, so that n minus 1/n. And 2 times n choose 2 is n times n minus 1. Okay, that's 2 times n choose 2. If you multiply with this, you get 1/n. And of course, that simplifies to also 1. Any question? So this is a rather interesting random variable that basically, right, is expectation equals to its variance. Doesn't matter, right, what n is. So there is this result, we won't deal with this here in this course, but it's called asymptotic distribution. Meaning when you take some number to go to infinity, but as n goes to infinity, as the number of people, right, number of people throwing the hats together, right, goes to infinity, what do you think the distribution of x approaches? What kind of random variable has expectation equals to variance? Well, the only one that you know of is a Poisson, right? A Poisson lambda has expectation lambda and variance also lambda. So of course that's not the reason at all, right? It's just very suggestive only, but it is true, and it's actually surprising that the distribution of the number of people getting the right hat as the total number of people goes to infinity approaches a Poisson one. Okay, random variable. All right, any question? All right, so with this, we're done with chapter 2, and we're going to move on to chapter 3 soon. But before, right, we do that, I want to say a few things. So regarding the midterm next week, this is the materials cap. In other words, right, midterm 1 will focus on questions in chapter 1 and chapter 2. I don't offer any review, preview, practice exams, whatever, right? Study your homework, study lecture notes, understand everything, and you do fine. You don't study or you don't understand the lectures, etc. You won't do fine. Okay, that's all there is. Now, because this is an online class, so again, right, let's maybe also say about the exam is well, it's during class time, right? But it's only 80 minutes. So next Friday, right? So the class is 2 hours, right? So that's I don't know, 40 minutes extra. So the first 40 minutes, I'll be here just for questions and answers. Again, I'm not gonna review anything. Bring your questions, right? It's basically, if you have any questions about any materials, you can ask questions. Well, I'm not gonna be here. I will be in the office hours link, okay? Because it's more like an office hours thing. If not, you don't have to be there. The exam will start. Well, the class starts at 2 o'clock, right? So the exam starts at 2:40. Okay. And to be collected at 4 p.m. Right? That's 80 minutes. Okay. And again, right? Well, not again, but so that's that. So in terms of the online environment, there are certain rules that you must follow, okay, for the exam. And I know that I posted the instruction, right? But I think from my experience, it doesn't hurt to go through it with you guys in the lecture. So let's take a look at that. All right. So this is your class. Well, you will see something similar to me. I don't know, see if you're a student. So if you look at the assignments, right? So, well, you see that you have the midterm equipment check, okay? So your actual exam will be very much like this. You'll have two assignments. One of them, well, it's not going to be equipment check anymore, right? Just midterm one is the actual exam, right? You'll do it there. This requires a lockdown browser, right? And responders. So which will record, right, your activity during the exam. One thing with lockdown browser, of course, is it's going to lock down your browser. So I found that from my past experience, submission is kind of a hiccup with lockdown browser. So there will be a separate assignment. If you click on this, there's nothing there, right? It's like your quiz. It's for submission only, okay? So what happens is after you're done with lockdown browser, you can close it, right? And scan your exam, or you can scan with lockdown browser on, that's fine, right? We'll talk about that. But basically you have 10 minutes, okay, extra beyond, right? The 80 minutes or beyond the moment you pull out your phone or whatever thing you use to scan to submit, okay? So 10 minutes, the clock starts counting from the time you take out your phone, okay? Remember that. So these are two things. The actual exam, the exam will be a PDF file with, problems in there. So you have to log into this assignment to see what the problems are, all right? And again, right, these things are designed to show you what your actual exam might look like or will look like actually, right? So this is for your practice, but of course, it's also for you to check your equipment to make sure they work, including internet, webcam, whatever, right? In terms of specific things to pay attention to, let's see here. The one thing, so this is blah, blah, blah. The one thing, well, you can bring the notes, right? But do not write down any worked out solutions. You will have to submit, right? Again, copy of your note together with your solution, okay? So that's how I will verify that you do not have anything on your note besides formulas and stuff. So formula means, let's say the moment chain function of Poisson, yeah, that counts as a formula. But let's say solution to problem 2.31 is not, okay, a formula. Second thing, and this is a big thing, and I think it's more like the iPad kind of thing, right? Students these days like to use tablets, let's say, to take notes, which is fine. You are not allowed to use any electronic devices. I mean, of course, besides the computer, you'll be, logging in, right? Lockdown browser and things like that on the exam, okay? So basically, paper and pencil or paper and pen activities only, okay? Along with that, we don't need to see your face beyond, right, the initial check. So we need to see your face to make sure you are you, right? You're taking the exam, you must show your ID, etc. But after that, what we need to see is your working area. Meaning, right, like right now, what you're seeing is you're not seeing my working area, you're seeing my face, okay? Working areas down below. Again, that's to show, basically, we need to see your hands, we need to see what you're writing. I mean, well, not that clear, but we need to see that you're writing on paper, etc. Okay. The reason, of course, is that, right, if the working area is not shown, then students might be accessing some other device on another screen that's out of the view of the webcam. Is that okay? So this is to prevent that from happening. So after you do the initial check and you show your working area, then we can verify that you are doing the work on pen and paper. So clearly, right, no cheating can happen that way. But if we can only see your face, then who knows what you're accessing at that time. Is that okay? On a second computer, whatever. So that's very important. You must show your working area during the entire exam. And then scanning and submitting. Oh, one more thing, right? To prevent people from, I don't know, adding stuff, right? After Lockdown browser is closed. Of course, 10 minutes is one way, but after you're done, you will be asked to hold up, right? Where was it? Show your work. And then take pictures. What this will be used for, and by the way, right, this the formula sheet also counts here. What this will be used for is it will be used to kind of correlate, right, with your submission to make sure that your submission is the same as what you show after you're done with your exam. Okay, so if you add anything extra, the show your work step will catch that. Or in other words, you cannot skip the show your work, right, step. Okay, this will be checked on the recording. Make sure you include your picture ID in the submission. All right. You will have an ID check during the first phase of Lockdown browser, but make sure you also include that in the submission. So, and again, right, the what was it? Equipment check is to kind of make sure you go through that. For the equipment check, several things to note here. I think the number one thing is make sure, right, you do it by next Wednesday. You're not required to do it. It's extra credit. So if you don't do it, it doesn't hurt. But if you don't do it, well, equipment not functioning, whatever, will not be accepted as an excuse because you didn't even check the equipment before, right? Including internet. Slow internet is not an excuse. So yeah, so there's no makeup, all right? So I have had people in the past pass the equipment check date asking for that assignment to be open. Not gonna happen. Yeah, you get extra credits for, basically going through the equipment check and kind of treat it, right, as an actual exam. Again, the reason is because, right, it will kind of show you if there's any step that you should pay attention to, and if something's not proper, you can correct it, right, before the actual exam. So you get rewarded, I guess maximum of 4 points, right? Extra credit. This is 4 out of 100. Okay, the exam will be out of 100 points. I do not know how many questions there will be on the exam. It'll be scaled out of 100, so 4 points extra out of 100. So there, right? That's all I want to tell you. Any question about any of these setup? All right, so that's it then. Let's continue on with the lecture. Okay. So the next chapter, chapter 3, will be conditional probability and conditional expectation, or let's just call it conditional distribution. All right. So again, you see the materials will build up, in this textbook, right? From basic probability to random variables, how random variables interact, and then now to conditioning, which, as I said, will be the cornerstone, right? Will be the key to understand stochastic processes. So you must master conditioning very, very well in order to be able to do stochastic processes. And this chapter will make sure you at least are exposed to that. So let's kind of talk about the general idea, right? The general idea of conditioning, right, again, is that if you have two events, E and F, then probability of E given F is defined like this, right? Of course, requiring that this is true. And so it talks about, right, the likelihood of E happening. Right, this is E, this is F, right? The likelihood of E happening given the knowledge that F has happened. But this is limited, right, to just, let's say, events. Chapter 2 talks about random variable. So you could talk about this kind of thing, probability that X less than equal to a given value, condition on Y less than equal to another value. Okay. Now, this, right, is just exactly, conditional probability, right, of E given F, because X less than equal to F is an event, Y less than equal to Y is an event, right? Well, but then you can move on to something a little bit more sophisticated like this. Probability X less than equal to X given Y equals to Y, let's say. Now, this is tricky because here, and let me just say, let me put this in quotation mark. The reason, right, is because when you condition, one of the important requirement is you don't divide by 0, of course. But here, right, if Y is a continuous random variable, then, right, you cannot, then probability, right, Y equals to Y, Y equals to little y is equal to 0. So technically speaking, this violates, right, the definition of conditional probability. So this cannot be a conditional probability to begin with. Well, let me explain why we still want to talk about it anyway. The reason like this, right? When we move to the random variable context, then by X and Y, we mean, kind of value. Let's say, I don't know. Let's say that, right, this is the arrival time, right, of a person to the train station. And this is like, I don't know, the number of people, right, the person sees on a platform, whatever, right? Now, the arrival time of, the time, right? Time is a continuous random variable. Let's just say that, right? Like you can model arrival time of a person to a train station as a uniform random variable or whatever, exponential. The key is that, right, is a continuous random variable, right? However, right, the person will arrive at the train station at a specific time. So it makes sense, right, to say that, oh, I know the person arrives at a certain time. Of course, you can also say the person arrives on or before a certain time, on or before, that's fine. But it's not strange to state this. Or in other words, right, basically here, the interpretation is you observed the value, right, of the random variable. Okay. And you asked about the distribution of x based on the observed value of y. All right. That's what you're asking. So you're asking for the distribution. Oops. Okay. So again, it's about information. If you do not observe y, or as you will see, if x and y are independent, then observing y does not affect how you believe, right? Your belief on the likelihood of x, or the distribution of x is not affected by the observation of value of y, if they're independent. But in general, right, if you observe y, it will change the likelihood of how you think of x. Therefore, the distribution of x will be influenced, right, by the value of y. So in general, there's a concept of conditional distribution. And in general, we write something like this: x conditioned on y. Okay. And it's a random variable. And it's very, 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 I can say very, very 10 times, because from my experience, to be easily confused when you do this kind of conditioning, because you know the randomness of y, the randomness of x, etc. Everything will be quite, let's say, subtle, right? So again, let me say this without exaggeration, advertise for the difficulty of chapter 3 and yet the importance of it, etc. Okay, in moving forward to understand stochastic process. So without further ado, right, let's jump in. And the easiest place, I guess, to look at the case when both x and y are discrete. Okay. The reason is if x and y are discrete, then we can avoid this awkwardness that I was mentioning, because then they can take on individual values. So we can talk about the conditional probability of x given y of a real value of x given the value of y. Okay. So all this is just a fancy notation to say this is probability of x equals to x, condition y equals to y. Right. And if you follow the definition of conditional probability, then that's like that. All right. Now be very careful. Be very careful to not go any further with this. For example, right, not split this into product, because, right, you cannot do that unless you know that x and y are independent, which again, right, it should not be the case here, because if they're independent, this will cancel and we just talk about the probability of x, the marginal distribution of x. So it's trivial for conditioning. So it's not going to happen, right? Very often at all, and not at all. The second thing to notice is that this is not as mundane as you think. This is not just marching out the formula and say, yeah, that's that. The real meaning of this is as follows. The first thing is you should look at this like this: dot conditional y. The difference is this, right? The dot here will tell you that in general, you're changing the x, but you fix the y value. So x here is the variable, and y is fixed. All right. And so again, the idea is, right, going back to you observe a value of y. So it's fixed here, right? You observed. And then this x is just different scenarios you're considering given that observed value. Is that okay? And the second thing is to remember, right, that this is related to, I was explaining, I think in chapter 1, right, is one of the topic in Ross, which is that this condition on f is a probability, right? Is that concept. In other words, if you can condition on a fixed event, then changing, right, different events that you condition on that fixed event is a probability, meaning it behaves like probability, right? All rules of probability applies to it. Therefore, right, going back to this context, this is, right, a distribution because it behaves like a probability. So this thing is literally distribution of x based on observed value. All right. The only thing that's different is eventually we'll replace this y by a generic y, like a random variable y. We'll get there later, right? For now, both of these values are constant, but they have very different meanings. This is a fixed value. That's what's being observed. This is a variable value. This is what's being changed, okay? That's different scenarios of x. Right. So yeah, right. So for example, then the textbook, right, write down this thing. This is the conditional CDF, right? Of x given y. Well, this is the conditional PDF. But PDF here means probability distribution function. It's not probability density function, okay? It's probability distribution function. But anyway, right, this is going to be the sum of all values less than n of the conditional probability. Like that. All right, so again, let's see what the meaning of this is, or what's the significance of this is. This is a mundane formula. It's not going to be used in problem solving. But once again, it tells you, right, what I was telling you before, that the meaning, right, is y is a fixed value, right? Notice in this sum, y stays the same, right? You observed the y value, it stays the same. What you're summing over is summing over this part, which is the variable. And then, right, once you recognize that, then this is just the usual summing, right, the probabilities below the value to get to the cumulative, right, distribution function. So nothing strange about that. The only thing that you should pay attention to is how the y gets fixed in this process, right? And again, it's that thing. The next one is conditional expectation, which is super important here. We don't deal with this very often, but this you can be guaranteed that we do. It will be the sum over all values of x times the conditional density, conditional distribution function. Right, so this is conditional expectation of x given y. Of course, right? Because this is so, you can also write as, but you know. So once again, right, what's the significance here? The significance here is if you hide this, then that's just good old expectation, you see. So the formula is deceptively simple, but trust me, it's not, right? In application. Again, it has that flavor of fixing the value of y and let x change. And we're in business as if, this is a regular random variable. So I guess maybe let me say this, right? Conditional distribution function is a proper distribution function, just like conditional probability is a probability proper. Okay. Again, that statement sounds a bit weird because what we're saying is when you fixed what you're conditioning on and let the other change, that it behaves just like the usual object that you know. Okay. I think there's also the formula for conditional variance. Well, you know what? They don't give it. I guess because I think they're into conditional expectation right now. Well, you know what? We're time's almost up anyway, so let's just throw a quiz here and then we're gonna be done for the day. This is quiz 9. For this case, right, for the discrete case, write down what you think is the conditional variance. If you can write down, that sort of shows that you understand how, at least have some initial idea of how conditioning works, how conditional distribution is, that works. If not, then you should think more deeply about this topic. All right, so what's the answer here? So you remember, right? Variance of x is expectation of x squared minus expectation square of x, right? And so conditional variance works in the same way. Conditional variance is expectation of x squared conditional y minus expectation square, or that's the expectation of x given y squared, right? Like that. Which is what? Well, we know what this is. This is this term squared, right? What are this? Guess what? It works in the same way, which is x squared, but now times the conditional probability summing over all x. That's this. So again, you see it all works with the conditional distribution. The other formulas follow the same way. And then the sum squared, like that. That's conditional variance. All right. So again, right, the purpose of this question or this formula is to ask if you understand what's really important about conditional distribution, which is this guy right here. All right. Everything else is determined by it as if we're working with the regular random variable. All right, so I think this is a good place to stop. If you have any question, I'll be happy to answer. If not, I'll see you next Monday. You too. Thank you.